All right, we're moving on to 3.3. Enough of that derivative definition stuff. That takes too long, too much algebra. So now we're going to move into the regular rules of differentiation. These are all the shortcuts that we've talked about. Let me first, before we do anything, let me show you some notation that the book uses. They put this d over dx notation in front of a function. I'll explain what this means in much more detail later. Don't worry about it right now. And then they have an equals something. So how we read this is when you see this here, that's just the derivative of this thing. So how I would read this is the derivative of 2x is 2. That's how they're showing this. And it's all throughout the book. So when you see this, don't panic. It's not a fraction. It doesn't mean anything like that. Just read that as the derivative of. Okay. So having said that, when you're looking in the book, then you know what that means. Let's look at our very first rules here. Our very first rule is the constant rule. So how we read this is the derivative of any constant is always 0. Why? Well, think about this. If you have, for example, y equals 2, that's a horizontal line, right? And it's a horizontal line from negative infinity to positive infinity. What's the slope of a horizontal line? It's always 0, no matter where you find, no matter where I'm looking, whatever x value. So that's just the case. Any constant is always 0. Doesn't matter what it is. So, for example, if I say, hey, f of x is 8, then f prime of x would be 0. The derivative of this is 0. Pretty simple. Next one, the most famous one, arguably, is the power rule. And the power rule says the derivative of a power function, meaning x to some number, to some power, is this. Notice you bring whatever the power was down in front as a coefficient. You bring it down, and then you subtract 1 from the power and leave it there. So again, you bring that value down in front, whatever the n was, and then subtract 1 and replace it with that. So let me give you an example. So if f of x is x cubed, then the derivative is bring that 3 down in front. So notice the 3 comes down in front as a coefficient. And then you subtract 1 from this and replace it. So 3 minus 1 is 2. Bring the 3 in front, 3 minus 1 is 2. And that works even if there's fractions, even if there's other things, even if they're negative numbers. We'll see some examples of that. So that rule is just take away 1. That's the power rule. So if I put those two kind of together, this rule says that if you take the derivative of a function that's multiplied by some kind of a constant, you can pull that constant out in front and just leave it there, and then just take the derivative of the function itself. So going back to our last example, we had x cubed, right? Well, in this case, I'm going to put a 2 in front of that x cubed. And so then notice this 2 is not going anywhere. So when I do my power rule, the 3 is going to come down here, and I'm going to multiply by that 2. So it's not going to become 32 or anything like that. It's 2 times whatever the derivative of that was. Well, the derivative, we just did it. It's 3x squared. So that's 2 times 3x squared, which is 6x squared. So this comes down and multiplies by whatever's there. Again, it can be negative numbers. It can be fractions. It doesn't matter. Just that process of bringing that down. Okay. Our next fairly simple rule is sum and difference. I'm just showing you the example of a sum here, but I'm sure you can understand differences too. So if I take the derivative of 2 functions added together or subtracted, as the case may be, you just take the derivative of each of them separately and add or subtract them as needed. So for example, if I have f of x equals 3 plus x squared, 2 functions here, you just take the derivatives of each of these separately. So the derivative of 3 is 0. The derivative of x squared is 2x, and you just add those together, and that's your derivative. Next is our first challenging one, and this is mega important. I might even put hyper mega important because you're going to use this all the time, and you do need to memorize this, but it will be memorized by you because you use it so much. So this is something right now you need to put on a note card, this and the next one, the quotient rule. So using the book's notation, it looks like this. So the derivative of f of x times g of x, multiplying 2 equations together, is f of x times the derivative of g of x plus g of x times the derivative of f of x. That's what that looks like. For our purposes, we change this. We make a little shorthand. That's a lot of writing there. So we just change these f of x's and g of x's to u's and v's. So the first function is a u function and then a v function. I made a table over here so you can see what we're doing. So when I say u times v, I want the derivative of u times v. That's going to be u times v prime plus v times u prime, where u is v of x, u prime is f prime of x, v is g of x, and v prime is g of x prime. So this is the notation I use right here. We're not using this notation, it's just too much to write. Let me give you an example, because you need one right now. So let's say I have this product here. I have this function, x squared plus 2. I have a binomial here times another binomial. Now you could say, hey, wait a second. Can't we just multiply those and then take the derivative using the sum or difference rule? Yes, you certainly can. And in this case, it wouldn't be that bad. It's just, you just use the FOIL method. But this is just a binomial, but it could be a trinomial. It could be two trinomials. It could be something we don't really want to do algebraically. And maybe you don't want to do it algebra. That's why we have this product rule available to us. So you have different ways you can go with this in as far as how you want to solve it. In this case, let's use the product rule. So here's what I am going to ask you to do. Later on, when you get good with it, you can use your own method, but we call this the plug and play method. So when I say plug and play, what I mean is the plug part is you're going to find all the bits of data you need to plug into a formula. Once you have them, you put it in the formula, and then we have played. The answer is there for you. So in this case, I need these 4 pieces of information, these 4 data points, the u, the v prime, the v, and the u prime. U is this, and v is that. So notice I'm making this little kind of a table here. I write the u over here, the v over here, and then below them, I'm going to write the u prime and the v prime. So I look right at this function. What's the derivative of x squared plus 2? Well, the derivative of x squared is 2x, and the derivative of 2 is 0. So the answer is just 2x. Over here, what's the derivative of 3x cubed? Bring that 3 down and multiply. That's a 9. Subtract 1, that's x squared. What's the derivative of 5x? Well, this is a little tricky, my friends. Remember, if I just have x here by itself, it's really x to the first power, right? Well, if I take a derivative, doesn't that 1 come down here and multiply by the 5? But then doesn't this become a 0? 1 minus 1 is 0? It does. So this becomes a 1. So the derivative of 5x is just 5. All right, so there's our derivative. Then here's my 4 data points. I just plug them in. There's the u, there's the v prime plus v u prime. Please don't simplify. You realize you simplifying this would take more time than it would be to multiply that in the first place. Just leave them right there. Thank you. Okay, that's the product rule. Now we have its analog, which is the quotient rule. Equally as important and even trickier. So the derivative of u over v is v u prime minus u v prime over v squared. So in this case, let's say we have an example. Here's 5x squared over 4x plus 3. We're going to do our same thing, our same plug and play. Make a table. So here's my u, there's my v. Take the derivative. Derivative of 5x squared is 10x. Derivative of 4x plus 3 is 4. Take those 4 pieces of information and plug them into our formula. Here's the v, u prime, minus u, v prime, all over v squared. All right? And that's it for the rules. All right, now we're going to go over some examples for our new rules we've learned. So checkpoint 3.12. So it's just, what is the derivative of x to the 4th? Well, bring the 4 down, subtract 1. So 4x cubed. Pretty straightforward. Checkpoint 3.13. Same thing, x to the 7th. Bring the 7 down. 7 minus 1 is 6. I think you get that, that process. And then 3.14. So here we have, we're going to do the sum and difference plus the constant multiple. So we have kind of a bigger function here. Remember, we just take the derivative of each piece separately. You don't need to worry about it. Just each one gets its own derivative. So the derivative of 2x cubed is 6x squared minus derivative of 6x squared is 12x to the first. I put the 1 there, but it's to the first. You don't need to put that there. And the derivative of 3, remember the derivative of a constant is 0. So then our answer is 6x squared minus 12x. This 3.15, this is a super common question. And so we're given a function, and it says, what is the equation of the tangent line to this function at x equals 2? We've looked at it graphically before, but we've never actually found what it is. So it's pretty straightforward. We just need to do two things. I have to find the slope at that point, which we know what to do. We need to take the derivative. And then just find the y-intercept of that line. And then I can write the y equals mx plus b form. So here's our function. So first thing we need to do is take the derivative. And for most of Calc 1, every time we have any kind of problem, it's going to involve the derivative. So you might as well just take it when you see it there, because you're going to need to use it in some form. So in this case, the derivative of 3x squared minus 11 is 6x. And in this case, we want to know what's the slope at 2. So I plug 2 into my equation here, and I get 12. So that's my slope. So now I'm thinking of y equals mx plus b. Well, that's my m, 12. So I have y equals 12x plus b. Well, I know that my x value is 2. So I can plug that into the original equation to find the y value at that point. I need a point. And so what's the point here is plug in 2 here. 3 times 4 is 12. 12 minus 11 is 1. So that's the point we're talking about. There's my x and y value. So then I can plug that right into here. So I get 1, y equals m, x plus b. And so that looks like 24. And so then the answer is negative 23. And so my answer is y equals 12x minus 23. That's the equation of the line that's tangent to this curve at 2. All right. And then let's see, 3.16. This is a product rule. In this case, I don't know. I'm just distributing that. I might as well just distribute that. You certainly could. Remember, there's more than one way to do this. But in this case, they want us to do the product rule, so we will. Here's my u. Here's my v. Copy those down. Find u prime, v prime. Well, the derivative of 2x to the 5th is 10x to the 4th. The derivative of v prime is 8x plus 1. Remember, taking the derivative, this is x to the first power. 1x to the first power, right? Okay. And then plug it in. U v prime plus v u prime. And apparently my world is at a slant there when I wrote that. And then, as you can imagine, the next one, 3.17, would be a quotient rule problem. There's my u and v. Go ahead and plug those in. Here's the derivative of u. Here's the derivative of v. And then plugging into this formula, so I have v u prime minus u v prime all over v squared. And again, please don't bother simplifying. It might distribute if you look in the back of the book, because they do simplify, but you'll have to figure out if it's equal or not. But simplifying, it's going to take more time than it is to solve it. Ooh, a tricky one. So we have f of x is 1 over x to the 7th. You might think that we want to do a quotient rule here, but remember, 1 over x to the 7th is the same as x to the negative 7. So, can we use the power rule with negatives? Yes, you can. So in this case, I'm going to bring that negative 7 down and say x to the negative 8. Now, I think you can see that a lot of times we're going to say, x to the negative 6, because 7 minus 1 is 6. No, we're going negative, right? We're moving that direction. So that's a common mistake. If you needed to return this back to its form that looks like this, it would be negative 7 over x to the 8th. It would be what that looks like. Skipping 3.19, I don't know why, but we'll have to see. So this is similar to the problem we did before. Here's a function, a curve, and they want to know when is this curve parallel to this line? When is this curve parallel to that line? So basically, when two items are parallel, they have the same slope. We know what the slope is of this line. It's 2. Okay, so basically what we're asking is, when is the slope over here going to be 2? That's what we're asking. So we find the derivative. So 8x minus 3. And then we set that equal to what the slope is we're looking for, because we want to find the x value that generates that slope. So I solve that and I get 8/5. So this curve here, at 8/5 has a slope of 2, which is parallel to that. Alrighty, friends.